start. Friends, as my friend Prof has introduced me, in fact he has taught me a couple of subjects. That's related with my PhD. I did my master's degree in 1976 and then switched over to instrumentation. For a couple of years I was in international rectifiers, manufacturing power semiconductor devices. So I used to work on a project called non-destructive receiver power semiconductors. All of you know that when you get a job, if you have a function like y equal to f of x, and you want to draw this function where x is a dependent variable, independent variable, y is a dependent variable. You can draw it in a graph with this can be some function y with f of x. It could be y equal to mx, or it could be y equal to mx plus c, or whatever it is. Or it could be y equal to minus mx plus c. One is that to draw these functions, we require a graph with only two dimensions, x and y. So y is a function of x, and if x is a quantity which is varying, y could be input in this amount. But what happens if the function is dependent on two variables? To give an example, we take current of a transistor, is a function of base current and right? This cannot be plotted on a single graphic. Because for one graphic, you can only plot a function of a fixed VC. You can plot the function of IC equal to f of LT or VC equal to 1. VC equal to 1. But what happens when the VC start varying 1, 2, 3, 4, and 5? You get multiple graphs. And that's how you get transistor characteristics in two dimensions. But that's really not the right way to plot. If you want to plot a function of two variables, y equal to it's like this. So y equal to f of, or I think it's a z, the function of x and y. Then you require a three-dimensional viewing facility. Are you with me? So you need to plot also the z-axis. Now you have to talk about a three-dimensional space. This is x, this is y, and this is z. The instrument that is set up here is known as RICTRON. WRSC stands for Western Regional Instrumentation Center. That's WRSC RIC. And Tron is like, electron, neutron, whatever. That's so we have put up RICTRON. Now, what does this setup do? This has a microprocessor board inside this. This unit is called RICTRON. It is the 885 board. Okay. Next, this is a power supply. This is a 3D plotter. It takes three inputs and plots it on a two-dimensional oscilloscope. So oscilloscope is used in the XY mode. So these are X and Y, so it goes from here, and there are three channels, V1, V2, V3. So you get a three-dimensional figure from the electron. There are three wires, cables. They come to this 2D plotter and then gives it 2D image. Now, why is it required? If you want to really study any physical system, very rarely that you will find that it is dependent on only one parameter. It depends on one number of parameters. So ideally speaking, you require something like an n-dimensional vector space where you can see a point in that space. You can see some of the photographs, and that's the reason I started with this presentation first. It's a product which is called an embedded graphic system. We have a three-dimensional graphics narrated using conventional microprocessor board. Let's see some other photographs. This is something, this is an oscilloscope. We are using a text. The text is being written on an oscilloscope. You can see the text images. Right? I'll go next. You see a waveform being generated. This is a unique waveform. It has got one period of a staircase, followed by a ramp, followed by a square wave, followed by a rectangular wave. It's not possible to generate this waveform if you don't use a microprocessor board as a function generator. So you are trying to use a composite waveform generator using a microprocessor. Normally you have a sine wave or a triangular wave or a square wave, but you don't have composite waves like this. That is one period of square followed by a triangular or vice versa, any combination of this. This is possible only using a microscope or a microcontroller. These are called programmable functional networks, where the wave shape can be changed. The period is same, period is not altered. Period between this to this, this to this is the same. What you are altering is the wave shape. Okay. What's next we are? This is just the Ohm's law. V is equal to I. You take a resistor, it's got a characteristic, it will look like this. Let me see. This is characteristics in 3 dimensions. You have the z-axis along. So each curve is the ICBC characteristics in 3 dimensions. Normally what you see in the book, you find that all the curves are merged to each other. That is doing the slide show. Okay. Now you can see this is the conventional characteristic what you see for a transistor, where the y-axis is the collector current, x-axis is the VC, and you find 8 different curves are for the 8 different values of IB. But this is not a right way to see the graph. You should see this graph in 3 dimensions. Because while the IC is a function of IB as well as VC. So the right way to see is in 3D and not 2D. So let us see whether you have a 3D image anywhere. This is 3D FED characteristics. Sorry, these are 2D FED characteristics. This is a typical cubic structure where you've got a 5 by 5 by 5 matrix in on a Cartesian coordinate system and a cube. When you study semiconductor physics and you want to study the crystal structure, this is a typical waveform that we use for. Now you can find that there are some lines that are brighter. 1, 2, 3, 4, 5. Okay? Let's see one by one. What next is this in the pipeline? You can see there are diagonals. Where there are certain planes. Okay, come back to see.